Yes, the minimum separation between the transistor channel and the implant should be 2 lambda. Again, these are all the rules which we have adopted while constructing the layout for the corresponding stick diagram of NMOS inverter. So, and you can see on top we have a polysilicon to diffusion boundary which should be of 2 lambda. That is, from here to here it should be 2 lambda. Similarly, from here to here it should be 2 lambda, because polysilicon should extend towards the left and right hand side by 2 lambda in order to maintain the rule of polysilicon to diffusion boundary of 2 lambda. And one has to establish a buried contact if you are going for an implant is which is surrounding this depletion mode transistor, which is represented as an implant. We need to have a contact. As you can observe in the stick diagram, we have a contact that should be of buried contact. So we have placed a buried contact here which is of dimension 4 lambda cross 4 lambda. So this represents our depletion mode NMOS transistor with gate and drain shorted. So source of the depletion mode transistor is connected to VDD, and whatever the polysilicon that we have drawn here will be acting like a gate, and on top of N diffusion it resembles like gate is shorted with a drain terminal. And we are going to extract the output from the N diffusion, which we can see here at the output side. V out is represented here using N diffusion here. And coming to the enhancement type MOS transistor, again polysilicon layer is crossing the N diffusion layer with the width of 2 lambda. Similarly, N diffusion are also having the width of 2 lambda, and the separation between the polysilicon and the diffusion should be of 1 lambda. Separation between polysilicon and diffusion layers should be of 1 lambda, but polysilicon to diffusion boundary should be of 2 lambda. Don't get confused with that. This is the separation between the layer of the polysilicon and the layer of N diffusion, which should be of 1 lambda. And this enhancement transistor width to length ratio is 1 is to 1. Width to length ratio is 1 is to 1. And so you can have a transistor channel of length and width of 2 lambda cross 2 lambda. So this is how we can construct the layout for a NMOS inverter. So let me move on to the second example of our discussion. So as we have seen how to construct a CMOS inverter in the previous session, this is the stick diagram of the CMOS inverter, and the corresponding layout is represented here using the color hatching format as well as using monochrome and along with the lambda scale which is being used here. So you can see on top we have a PMOS device which is represented using the yellow stick with a green boundary, and on the bottom we have N diffusion which is represented using green color or green stick. And you can observe we have a contact at the VDD rail as well as VSS rail, and we also have a contact for the N diffusion to metal as well as P diffusion to metal and from metal to polysilicon. So together totally we have 5 contacts. So all those 5 contacts should be reflected in the layout construction as well. So coming to the layout, VDD and VSS rails will be of metal one, which are blue in color, represented as it is. And this is the VDD contact where N diffusion is running on top of the metal one, that along with the black color contact representation that represents our VDD point. Similarly for VSS, a P diffusion which is on top of metal one, and a black color square shaped box which represents our contact. And because this CMOS inverter construction is based on P-well process, NMOS transistor cannot be placed directly on the P substrate, sorry, directly on the N substrate. So we need to construct a P channel, sorry, P-well. So NMOS transistor is constructed on top of the P-well. So we require uh, P-well here, which represents which is purple in color, and Inside the P well, we are going to construct our NMOS transistor. And for P, PMOS transistor, which is on top, which is a pull-up transistor, we require N diffusion, and the polysilicon is crossing the N diffusion here, and this yellow color boundary represents our P plus mask. This P plus mask is used in order to allow the P diffusion to happen, or in order to allow the P diffusion process to undergo whenever we do the fabrication. So this is the color hatching representation of the CMOS inverter circuit, and on the right hand side you can see along with the dimension we have a monochrome format of the layout construction of CMOS inverter. So we'll move to the next example, that is CMOS NAND gate with two inputs A and B. So left hand side we have a stick diagram of what we saw in the previous session. Uh, for an AND gate, because we have a multiplying operator between variables A and B, PMOS transistor should be in parallel and MOS transistor should be in series. Similarly, if you have a addition operator between two variables A and B, it acts as a NOR gate with complement symbol. So in that case, PMOS should be of series, and MOS should be of parallel. So here we have a P diffusion which are parallel and N diffusion which are in series. So corresponding layout construction is done on the right hand side, keeping in mind the dimensions also represented here. You can see metal 1 with VDD of 3 lambda, similarly metal 1 on VSS as 3 lambda, and this is the minimum separation that one has to maintain between the polysilicon and diffusion boundary, and width of the diffusion is 2 lambda, width of the metal is 3 lambda, width of metal is 3 lambda, width of the end diffusion is also 2 lambda. And again here we have a poly to poly separation. According to the design rules, it should be 2 lambda, which has to be maintained. And similarly you can see here this dotted boundary represents our P well in which the NMOS construction is done, and this dotted boundary represents our P plus mask in which the P diffusion has to take place. And you can see the minimum separation between the poly to metal should be of 2 lambda. It can be greater than 2 lambda, but it should not be less than 2 lambda. So here where there exists a channel in which the polysilicon is crossing the P diffusion. Similarly, here exists a channel in which polysilicon is crossing the P diffusion. These two act as P1 and P2, that is PMOS 1 and PMOS 2, which are in parallel. And whenever polysilicon is crossing in diffusion, they again represents a NMOS transistor. Similarly, we have one more NMOS transistors. So all the feature size of both PMOS and NMOS transistors which are considered here in the NMOS construction are having the width to length ratio of 1:1. One has to keep that in mind whenever we start constructing the layout. So we'll move to the next layout, that is CMOS NOR gate. So this is the stick diagram for A plus B bar, that is NOR gate, two input NOR gate, and you can see PMOS are in series, NMOS are in parallel here, and polysilicon is crossing both PMOS and NMOS, and that represents inputs A and B, and the demarcation line which distinguishes between the P type MOS transistors with N type MOS transistors. Similarly, on the left hand side we can observe this yellow color boundary represents our P plus mask in which the PMOS diffusion has to take place, and this purple color boundary represents our P well in which the N diffusion is NMOS transistor is being constructed. And again we have a P plus mask here because we have a P diffusion which is on top of the metal one in order to establish VSS. So because we need to have P diffusion, it can only be done with the help of P plus mask. P diffusion can only happen with the help of P plus mask. So there is a 1:1 relation between stick diagram and the layout. The difference between stick diagram is stick diagram does not define the dimensions of the layers, whereas the stick diagram is going to denote only the color format or the color of each of those layers, like diffusion, implantation, polysilicon, metal, etc. So stick diagram is usually going to use the color encoding, whereas our layout is with respect to the lambda based design rule dimensions. So we'll move on to the next example. This is one of the most important stick diagram that we had discussed in the previous session, NMOS shift register cell. So on the left hand side you can see we have a, NMOS shift register. This will be a depletion transistor and this will be an enhancement transistor. This acts like an NMOS inverter, and the input to the NMOS inverter is passed on through a pass transistor which is of enhancement mode N type. So here we can apply the input. That input is applicable to the NMOS transistor of the NMOS inverter enhancement mode only if your clock signal is logic high. That is how the working of the shift register is uh, going to happen. So corresponding layout construction is on the right hand side. This represents our NMOS transistor, sorry, NMOS inverter with a length to width of say 4:1, and this is of length to width 2:1. So one can observe with respect to the width to length ratio how the sizes of the layers are going to differ. And this represents our pass transistor, and this is the inverter, NMOS inverter. From the pass transistor we are going to apply the input to the uh, NMOS enhancement type transistor, so that it gets reflected as opposite to that of input on the output side. So this in NMOS shift register cell is constructed with respect to the lambda scale on the x and y axis, and one has to follow the same design rules while constructing layout for any of the digital circuits. So last example which I'm going to consider in this presentation is a 1-bit CMOS shift register cell. So on the left hand side you can see a 1-bit CMOS shift register stick diagram which has a transmission gate in the first stage and one CMOS inverter in the first stage. Similarly, one more transmission gate in the second stage and one more CMOS inverter on the second stage. So this complete stick diagram represents a 1-bit CMOS shift register. Same concept is applied here, even construction of layout. So this entire thing represents our transmission gate, and this represents our the first stage CMOS inverter. This entire thing represents our second transmission gate, and this represents our second CMOS inverter. And phi 1 and phi 2 are our clock signals in order to switch the data or forward the binary data from one stage to the next stage. So with this, I'm going to end my presentation for this session. Thank you very much.